Somewhere in the universe, there is a place where light falls in and never returns. A place where time itself bends and slows and nearly stops. Welcome to the Sleepy Lab. Tonight, we will drift gently through the story of black holes, what they are, how they form, and what happens to time and space near their edges. If you haven't already, consider subscribing, one sleepy soul at a time. Now, let's begin. A black hole is a region of space-time where gravity has become so strong that nothing can escape. Not a spacecraft, not a signal, not even light itself. Once something crosses inside, it is gone from the rest of the universe quietly and completely. This idea, strange as it sounds, is not new. In 1783, a country clergyman and natural philosopher named John Michel sat with his calculations and arrived at a remarkable thought. He wondered whether a star could be so massive, so dense, that the light it produced would fall back down before it ever reached the sky. He called these objects dark stars. And though his methods were simple by today's standards, the core of his idea was sound. Light, he reasoned, could be trapped by gravity. This was more than a century before Einstein was born. The mathematics that describe black holes as we understand them now came later, in 1916, in the middle of a war. A German physicist named Karl Schwarzschild found an exact solution to Einstein's newly published equations of general relativity. Schwarzschild was serving on the Eastern Front at the time, and yet, in those conditions, he managed to describe the geometry of the simplest possible black hole, a perfectly still, perfectly round collapse of mass into a point. His solution revealed something strange, a boundary surrounding that point, a threshold with quiet and absolute authority. That boundary is called the event horizon. It is not a wall. It is not a surface you could touch or see. There is no material edge, no barrier of metal or stone. It is simply the point beyond which nothing that enters can ever return. A line drawn in the fabric of space and time by gravity alone. You could cross it, in principle, without even knowing. And yet, everything changes there. But we are getting ahead of ourselves. Let us first ask how such a thing comes to exist. A black hole of the kind Schwarzschild described forms from a star, but not just any star. It takes a star roughly 25 times the mass of our sun, a vast, luminous body that burns through its fuel over millions of years. When such a star reaches the end of its life, it can no longer hold itself up against its own weight. The core collapses. And if the mass is great enough, nothing can stop that collapse. Not the pressure of atoms, not the resistance of matter itself. The star falls inward, and what remains is a black hole, a stellar mass black hole, born from the death of something enormous. These are not the only kind. At the centers of most large galaxies, there exist black holes of an entirely different scale, supermassive black holes containing millions to billions of times the mass of our sun. They sit quietly at the hearts of galaxies, ancient and patient. Our own galaxy, the Milky Way, carries one at its center. It is called Sagittarius A star, and it holds a mass of about 4 million suns, all compressed into a region smaller than the orbit of Mercury. In 2019, for the first time in history, we saw one. The Event Horizon Telescope, a network of radio dishes spanning the globe, captured the shadow of a supermassive black hole in the galaxy M87. It appeared as a dark circle surrounded by a glowing ring of hot gas. Not a photograph in the usual sense, but a reconstruction of radio waves gathered from across the Earth. A quiet confirmation of what mathematics had predicted for over a century. Now, there is a common misunderstanding worth setting down gently. Black holes do not reach out and pull everything toward them. If you were to replace our sun with a black hole of exactly the same mass, the Earth would continue in its orbit as though nothing had changed. The sky would go dark, yes, but the gravitational pull would be the same. The planets would not spiral inward. They would simply keep drifting along their familiar paths around an invisible center. A black hole's gravity only becomes inescapable once you cross the event horizon, not before. From a distance, it is simply mass, curving the space around it the way any mass does. And that curving of space creates something beautiful. From far away, a black hole bends the light of stars behind it. The light does not vanish, it is redirected, stretched into arcs and rings, sometimes producing duplicate images of the same distant star. This is called gravitational lensing, and it turns the black hole into a kind of lens, reshaping the sky around it in soft, luminous distortions. There is another effect, perhaps even more remarkable. Einstein's general relativity tells us that time itself runs slower in stronger gravitational fields. This is not a metaphor. It is not a trick of perception. It is a measured, confirmed feature of the universe. It is called gravitational time dilation. A clock placed near a black hole ticks measurably slower than an identical clock resting far away in open space. The stronger the gravity, the slower the passage of time. And near a black hole, gravity is very strong indeed. So if you could watch two clocks, one beside you and one drifting near that dark horizon, you would see them disagree, slowly at first, then more and more. The one near the black hole falling behind, as though time there had grown thick and heavy. And this is real. This is the universe we live in. Let that settle for a moment. Time, bending near the edge of darkness. Now picture someone falling toward one of these immense black holes. Not a small one, not a collapsed star, but a supermassive black hole. The kind that sits at the center of a galaxy, holding billions of solar masses in its quiet grip. An astronaut drifting towards such a black hole would experience something deeply counterintuitive. At the moment of crossing the event horizon, that invisible boundary from which nothing returns, they would feel nothing unusual. No wall, no barrier, no sudden change. The crossing would be gentle, even unremarkable. Space around them would look curved, yes, and the stars behind them would be warped and strange. But there would be no sign, no signal, no alarm to say, you have just passed the point of no return. And yet, for someone watching from a safe distance, the story would look entirely different. They would see the astronaut drifting closer and closer to the horizon, and then beginning to slow. Not because the astronaut is slowing down, but because the light carrying their image is struggling harder and harder to climb out of that gravitational well. The astronaut would appear to move more and more slowly, their image dimming, reddening, fading. They would never quite seem to reach the horizon, just an ever fainter silhouette, frozen at the edge of darkness, growing dimmer and dimmer until they vanish from sight altogether. Two versions of the same event, one felt, one seen, and both of them true. The fading and reddening that the distant observer sees has a name. It is called gravitational redshift. As light climbs away from the intense gravity near the event horizon, it loses energy. Its wavelength stretches. Blue light becomes red light becomes infrared, and eventually the light stretches beyond what any instrument could detect. The astronaut is still there, still falling, but their light has been pulled so thin that it simply disappears. This is what gravity does to light near a black hole. It does not just bend it, it stretches it, it exhausts it. Closer still to the black hole, there is a region where light does something even more extraordinary. It orbits. This region is called the photon sphere. It is not a surface. It is a shell of space at a precise distance from the black hole where a beam of light, if aimed just right, would travel in a circle, looping around the black hole in an unstable orbit, not falling in, not escaping, just circling for a moment. The orbit is unstable, which means the slightest disturbance would send the light spiraling inward or flying away. But at that exact distance, light balances on a knife's edge between capture and freedom. And if you could somehow hover just outside the photon sphere, holding yourself steady against the immense pull of gravity below, you could look straight ahead and see the back of your own head. Light leaving, you would travel all the way around the black hole and return to your eyes. A complete loop, your own image, delivered to you by curved space-time. It is a strange and quiet thought. Now, not all black holes offer such a gentle crossing as the supermassive ones. Smaller black holes, the kind born from collapsing stars, are far less forgiving, and the reason comes down to something called tidal forces. Gravity is not uniform. It pulls harder on whatever is closer. If you were falling feet first toward a black hole, the gravity at your feet would be stronger than the gravity at your head. This difference creates a stretching force, pulling you apart along your length while squeezing you from the sides. Astrophysicists have a real, published, technical term for this. They call it spaghettification. The body is drawn thinner and thinner, like a strand of pasta, stretched by the difference in gravitational pull from one end to the other. For a stellar mass black hole, perhaps 10 or 20 times the mass of our Sun, this stretching begins well outside the event horizon. Long before you ever reach the boundary, the tidal forces would be overwhelming. The human body would be pulled apart, gently at first, then catastrophically. It would be fatal far before any crossing could take place. But for a supermassive black hole, the geometry is different. The event horizon is so far from the center, and the curvature of space-time so gradual at that distance, that the tidal forces at the horizon can be remarkably gentle. Gentle enough that a human body could survive the crossing intact, passing through without being torn, without being stretched, drifting inward, whole and unharmed, into a place from which there is no return. And what waits on the other side of that crossing? Once inside the event horizon, the nature of space itself changes in a way that is difficult to hold in the mind. Every path through space-time, no matter which direction it points, leads inward toward the center, even if you turned around. Even if you fired the most powerful engine ever built, pointing directly away from the singularity, you would still move inward, because inward is no longer a direction in space. It has become a direction in time. Inside the horizon, the roles of space and time effectively swap. Moving forward in time, which you cannot help but do, means moving inward in space. The singularity is not a place you travel to. It is a moment you arrive at, as unavoidable as tomorrow. There is no turning back, not because you lack the speed, but because the very structure of the universe inside that boundary has folded in on itself. Every future, every possible path, converges on a single point. That point is the singularity. At the singularity, as described by general relativity, density becomes infinite. The curvature of space-time rises without limit, and the mathematics that so beautifully describes the rest of the universe simply stops working. The equations break. The predictions dissolve. It is not that we get a strange answer. We get no answer at all. This is where known physics ends. General relativity, the theory that predicted black holes in the first place, faithfully carries us all the way to this point and then falls silent. It predicts the singularity, but it cannot describe it. It can bring us to the edge of understanding, but not beyond. Most physicists believe that the singularity is not truly infinite, that it is a signal, a marker, telling us that our theory is incomplete. Somewhere in that extreme environment, where gravity is immense and distances are unimaginably small, a deeper theory must take over, a theory that unites gravity with quantum mechanics, something we have not yet found, something often called quantum gravity. We do not know what that theory will say. We do not know if the singularity will be replaced by something gentler, something finite, something strange and new. But most who study these questions believe that nature does not deal in infinities, that the singularity is a placeholder, written in the language of a theory that has reached the edge of what it can tell us. And so the center of a black hole remains one of the deepest mysteries in all of physics, a place where our best descriptions of reality admit, quietly, that they do not know. Let that sit with you for a moment. A place in the universe where even our understanding comes to rest. But not all black holes are the same. The simplest kind, The one Schwarzschild described does not spin, it sits perfectly still, a pure and motionless well in the fabric of space and time. But the universe rarely makes things so simple. In truth, nearly every black hole we know of is spinning. Some of them spin very fast indeed. In 1963, a mathematician from New Zealand named Roy Kerr found a new solution to Einstein's equations, one that described a black hole that rotates. And what he found was something far stranger, far richer than the still and silent black hole Schwarzschild had imagined decades before. A rotating black hole does not have just one event horizon. It has two. The outer horizon is much like the one we have already spoken of, a boundary of no return. Cross it, and you cannot come back. But deeper inside, closer to the center, there is a second boundary, an inner horizon, sometimes called the Cauchy horizon, a threshold where the predictable nature of space-time begins to falter, where the future, in a sense, becomes uncertain even to the equations themselves. And there is something else, something that exists outside the event horizon entirely. Around a spinning black hole, there is a region called the ergosphere. It is not behind the horizon, it is just above it, surrounding it like an invisible atmosphere. And within this region, space-time itself is moving. Not matter, not light, space-time. The very fabric of the universe is caught in the rotation of the black hole and dragged along with it, like water circling slowly toward a drain. But here it is not water. It is the structure of reality itself, turning. Inside the ergosphere, nothing can remain still. No object, no matter how powerful its engines, can hover in place. Everything is forced to move, forced to co-rotate with the black hole. You could fire your rockets with all the energy you had, trying to stay in one spot, and it would not matter. The space you occupy is already moving. You are carried along, gently and irresistibly, like a leaf on a turning river. And yet, strangely, you are still outside the event horizon. You could still escape. You could still leave and return to the wider universe. You are caught in the current, but not yet past the point of no return. In 1969, the physicist Roger Penrose realized something remarkable about this region. He showed that the ergosphere could be used, that energy could be extracted from a spinning black hole. The idea is elegant in its simplicity. An object enters the ergosphere and splits into two pieces. One piece falls inward, past the event horizon, lost forever. But the other piece is flung outward, away from the black hole, carrying more energy than the original object had when it entered. The extra energy comes from the black hole's own rotation. The black hole spins a little slower afterward, and the escaping fragment carries that stolen energy out into the universe. This is called the Penrose process, and in principle, it could allow a civilization, a very advanced and patient civilization, to harvest up to 29% of a black hole's total mass as pure energy, a slow and quiet mining of the cosmos, drawing power from the spin of space-time itself. We have never done this. Of course, we may never do it, but the physics allows it. The universe, it seems, has written the possibility into its laws. Now, there is one more kind of black hole worth mentioning, though it may be the rarest, a black hole that carries an electric charge but does not spin. This is described by what is called the Reissner-Nordström solution. It is mathematically beautiful, but in practice, real black holes almost certainly carry very little net charge. The universe tends to neutralize them quickly. Still, the solution matters, because it helps us understand the full landscape of what a black hole can be. And that landscape, it turns out, is surprisingly simple. There is a result in physics sometimes called the no-hair theorem, and what it tells us is this: a black hole, no matter how it formed, no matter what fell into it, no matter how complex the star or the cloud of gas or the collision that created it, is fully described by just three properties: mass, spin, and electric charge. That is all. Three numbers, and you have said everything there is to say about a black hole from the outside. Every black hole with the same mass, the same spin, and the same charge is identical to every other. There is no way to tell them apart. No fingerprint, no trace of what came before. All the richness of the matter that formed it, the elements, the structure, the history, all of it appears to be lost, swallowed behind the event horizon, erased from the outside universe. And this is where one of the deepest puzzles in all of physics begins. It is called the black hole information paradox. In quantum mechanics, information is never truly destroyed. The laws of physics, at their most fundamental level, are reversible. Every process, in principle, can be run backward. The information about how something began is always preserved, somewhere in the state of the universe. But a black hole seems to violate this. It takes in matter, rich with information, and presents to the outside world only 3 bare numbers. The rest is gone, or so it appears. For decades, this paradox has quietly troubled the deepest thinkers in physics. It sits at the intersection of gravity and quantum mechanics, the 2 great pillars of our understanding, and it whispers that they do not quite agree. Then, in 1974, Stephen Hawking made the puzzle even deeper. He showed, through a careful calculation involving quantum effects near the event horizon, that black holes are not perfectly black. They emit a faint glow, a whisper of thermal radiation, rising from the boundary between the inside and the outside. This is called Hawking radiation. It means that a black hole has a temperature, an almost impossibly low temperature, but a temperature nonetheless. It radiates, softly, into the dark. For a black hole formed from a collapsed star, this radiation is so faint, so cold, that it is far below the temperature of the cosmic microwave background, the ancient afterglow of the Big Bang that fills all of space. We cannot detect it, not with any instrument we have today. It is buried beneath the warmth of the universe itself. But it is there. The mathematics is clear. A black hole glows. Not with the light of anything burning inside it, but with the quiet hum of quantum fields at the edge of the horizon, where the fabric of space trembles just enough to release a single particle now and then into the night. Let that settle over you for a moment. Even in the deepest darkness the universe can create, there is still a glow, faint beyond measure, patient beyond imagining, but present. A warmth so soft it is almost nothing. And yet it is not nothing. And because that glow is there, because each faint particle carries away the smallest imaginable amount of energy, the black hole loses something of itself. It grows lighter. Not in any way you could notice, not in any span of time a human life could hold, but over ages so vast, they make the history of the universe feel like a single breath. The black hole slowly, quietly, gives itself back to the cosmos. This is what Hawking's discovery truly means. A black hole is not eternal. It evaporates. Particle by particle, photon by photon. It releases its mass into the surrounding dark, and with each tiny departure, it becomes a little smaller, a little warmer, a little closer to the end of its long, patient life. How long does this take? For a black hole with the mass of our sun, the time is almost impossible to hold in your mind. Roughly 10 to the power of 67 years. That is a 1, followed by 67 zeros. The universe, as we know it, is about 14 billion years old. 14 billion is a large number, but it is nothing beside 10 to the 67. It is a raindrop beside an ocean that stretches beyond every horizon you could ever imagine, and then beyond that, still. So the black hole waits. It radiates. It loses mass so slowly that for most of its life, nothing seems to change at all. The universe around it grows old. Stars burn out. Galaxies drift apart and go dark. And still the black hole sits, glowing with that impossibly faint warmth, releasing one particle at a time into the silence. But something curious happens as it shrinks. As the black hole loses mass, its temperature rises. A large black hole is cold, colder than almost anything in the universe. But a smaller black hole is warmer, and a still smaller one, warmer yet. So as the ages pass and the black hole slowly fades, it begins to glow a little brighter, a little hotter. The process that seems so impossibly slow begins, in its final stages, to quicken. In its last moments, the black hole is very small and very hot, and the radiation pours out faster and faster until, at the very end, there is a final release of energy. This is sometimes called a black hole explosion. But do not picture violence. It is not a detonation in the way we usually think of one. It is a quantum process, a last exhalation. The final particles streaming away as the black hole gives up the last of what it was, and then it is gone. Nothing remains. No horizon, no singularity, no darkness at the center. Just empty space and the faint warmth of those radiated particles drifting outward into the night. And here, something deeply troubling arises. When the black hole formed, it swallowed matter. Stars, gas, dust, all of it carrying information. The precise arrangement of every particle, every quantum state, every detail of what fell in. All of that information vanished behind the event horizon. And now the black hole has evaporated. It is gone. The Hawking radiation it released appears to be thermal, random, carrying no record of what the black hole once consumed. So where did the information go? This is the black hole information paradox, and it touches one of the deepest principles in all of physics. In quantum mechanics, there is a rule called unitarity. It says, in essence, that information is never truly destroyed. The past can always, in principle, be reconstructed from the present. Every process, no matter how complex, preserves the full record of what came before. If a black hole evaporates and the information is simply gone, unitarity is broken, and with it, something fundamental about the way the universe keeps track of itself. This is not a small problem. It has occupied some of the finest minds in physics for decades, and it remains, as far as we can tell, unresolved. But there are ideas. Some physicists propose that the information is not lost at all, that it is encoded, somehow, on the surface of the event horizon itself, written into the very boundary of the black hole in a way we are only beginning to understand. This idea is connected to something called the holographic principle. It suggests that all the information contained within a volume of space, everything happening inside, can be fully described by data on its boundary, on the surface that encloses it. Think of it this way. Everything the black hole holds, every particle, every quantum state, every detail of every star it ever consumed, all of it written on a two-dimensional surface, like words on the skin of a sphere. The inside described entirely by the outside. This notion has its roots in the work of Jacob Bekenstein. In the early 1970s, Bekenstein showed something remarkable about black holes and entropy. Entropy is a measure of hidden information, of all the possible arrangements a system could have that would look the same from the outside. And Bekenstein discovered that a black hole's entropy is not proportional to its volume, as you might expect. It is proportional to the area of its event horizon. The surface, not the interior. And the numbers are staggering. Even a small black hole, one just a few times the mass of our sun, carries more entropy than all the ordinary matter in the entire observable universe. All the stars, all the gas, all the dust, all the planets and moons and everything upon them, together, they hold less hidden information than a single quiet black hole drifting through the dark. This relationship was refined into what is now called the Bekenstein-Hawking entropy formula, and it is one of the most quietly profound equations in all of physics, because it connects three realms that usually stand apart. Gravity, the bending of space-time by mass. Quantum mechanics, the strange behavior of the very small. And thermodynamics, the ancient science of heat and order and disorder. All three meeting in a single expression written on the surface of a black hole. Let that thought rest for a moment. The deepest connections in physics, woven together at the edge of darkness. Now, let us step back from the horizon and look at what surrounds it. A black hole, left alone in empty space, is nearly invisible. But black holes are rarely alone. They drift through galaxies rich with gas and dust and the scattered remains of ancient stars. And when that material draws near, something beautiful begins to form. Gas and dust do not fall straight in. They carry momentum, a sideways motion, and so they spiral slowly, curving inward along long, graceful paths, gathering together into a vast, flattened disk that wraps around the black hole like a luminous ring. This is called an accretion disk. As the material spirals closer, it is compressed. Particles collide, friction builds, and the gas grows hot, hotter than the surface of any star, millions of degrees, glowing not in visible light, but in X-rays, pouring energy out into space with a brilliance that can be seen across the universe. All of this from matter that has not yet crossed the horizon, still orbiting, still spiraling, still caught in that long, slow fall. There is a boundary within the disk, a distance called the innermost stable circular orbit. It is the closest path on which matter can still circle the black hole without losing its footing. Inside that orbit, there are no stable paths. Matter that crosses this threshold has no way to hold itself in place. It plunges inward, swiftly and silently, toward the event horizon, with nothing left to slow it down. And so the disk has an inner edge, a place where the glow ends and the darkness begins, where the last light spirals inward and is gone. Let that image settle behind your eyes. A ring of light, impossibly bright, impossibly hot, surrounding a circle of perfect dark, and at the boundary between them, matter making its final journey, falling gently, steadily, into the quiet. But not all matter falls so quietly. Some black holes do something that, even now, we do not fully understand. They launch jets, narrow columns of plasma, fired outward from the poles at nearly the speed of light, not falling in, but streaming out, away from the black hole, away from the disk, away from everything, cutting through space like two long, thin beams of pure energy. These jets can stretch for thousands of light years. Thousands. A single stream of superheated matter, longer than the distance between our sun and its nearest neighboring star, many times over, reaching far beyond the galaxy that contains the black hole itself. They are among the most energetic phenomena in the known universe, and they are born at the edge of the deepest darkness we have ever found. How this happens is still a question we are carefully unraveling. The best understanding we have is that magnetic fields, threaded through the spinning accretion disk and wound tight by the rotation of the black hole itself, twist and coil until they form a kind of funnel, a channel. And along that channel, matter is accelerated to speeds that approach the fastest anything can travel, flung outward, even as everything around it falls inward. The spin of the black hole is what shapes them. Its rotation drags space-time, drags the magnetic field lines, and wrings energy from the disk and from the black hole's own angular momentum, all of it focused into two narrow beams, one from each pole, perfectly opposed, streaming into the void. Let that settle for a moment. A black hole, an object defined by its ability to pull everything inward, also capable of sending matter outward across distances that dwarf entire galaxies. There's a kind of quiet symmetry in that. Now, when a supermassive black hole sits at the center of a galaxy and feeds actively, consuming vast amounts of gas and dust, the region around it can become extraordinarily bright, so bright that it outshines everything else. Every star in the galaxy, every nebula, every cluster, all of them together, dimmed by comparison. These brilliant cores are called quasars, A single quasar, powered by one supermassive black hole swallowing matter from its surroundings, can outshine its entire host galaxy by a factor of 100 or more. 100 galaxies worth of light, pouring from a region no larger than our solar system, all of it driven by gravity and friction, and the long spiral of matter toward an event horizon. The most distant quasars we have found existed when the universe was very young, less than 1 billion years old, a time when the first galaxies were still assembling themselves from clouds of primordial gas. And already, even then, supermassive black holes had formed and begun to feed. Their light has been traveling toward us for almost the entire history of the cosmos, and it is only now arriving, faint, redshifted, ancient, but still visible. That light left its source in a universe that looked nothing like the one we know, a universe without most of the stars that exist today, without the Earth, without the Sun. And yet the physics was the same. Gravity pulled, matter spiraled, friction heated, and light poured outward from the edges of darkness. Some of that light is the last trace of stars that wandered too close. Every now and then, a star drifts near a supermassive black hole, not in a stable orbit, but on a path that carries it just close enough for the tidal forces to take hold. The side of the star nearest the black hole is pulled more strongly than the far side, and the difference is enough to tear the star apart. This is called a tidal disruption event. The star does not vanish all at once. It is stretched, pulled into a long ribbon of glowing gas that wraps around the black hole. About half of the star's material is flung outward, escaping into space, scattered and lost. The other half spirals inward, joining the accretion flow, heating as it falls, producing a flare of light that can be seen across billions of light years. A star, unmade, half of it swallowed, half of it set free. And then the flare fades, and the black hole is quiet again, waiting. Breathe gently now. Let your body rest a little deeper. There is another way black holes reveal themselves, not through light at all, but through something even more subtle. When two black holes drift close to one another, caught in each other's gravity, they begin to spiral together. Slowly at first, orbiting, circling, drawing nearer with each pass. And as they spiral, they disturb the fabric of space-time itself, sending out ripples, faint waves that spread outward in every direction, like the surface of a pond touched by something unseen. These are gravitational waves. Not sound, not light, but a gentle stretching and compressing of space itself, passing through everything, through stars, through planets, through you, without stopping, without slowing. For most of history, we had no way to detect them. They were predicted by Einstein's equations, but they are so faint, so impossibly subtle, that measuring them seemed beyond reach. And then, in September of 2015, we heard them for the first time. Two black holes, each roughly 30 times the mass of our sun, spiraling together about 1.3 billion light years away. They had been circling each other for ages, drawing closer, moving faster, until in the final fraction of a second they merged, became one. In that brief moment, the energy released was greater than the energy of all the stars in the observable universe, combined, not as light, not as heat, but as gravitational waves, rippling outward through the cosmos at the speed of light. By the time those ripples reached Earth, they had been traveling for over 1 billion years, and they were unimaginably faint. They stretched and compressed the distance between two mirrors by less than 1,000th of the width of a proton, and yet we measured them. After the merger, the newly formed black hole was not yet still. It trembled. It rang, the way a bell rings after it has been struck, sending out gravitational waves that grew softer and softer, a tone falling away into silence. This is called the ring down, the last vibrations of a new black hole settling into its final shape, each ripple carrying information about its mass, its spin, a kind of signature written in the bending of space. And then the ringing fades, and the black hole is quiet, perfectly still, as though nothing had happened at all. Two became one, and the universe barely noticed, except for those faint ripples still spreading outward, even now, passing through galaxies, through nebulae, through the empty spaces between stars, growing weaker with every passing moment, but never quite disappearing. Let that thought drift with you now. The idea that space itself can tremble, that the collision of two dark objects, far away and long ago, can send a whisper across 1 billion years, and that we, here on this small world, learned how to listen. And in that ringing, in those last soft tremors of a newly formed black hole, there is something hidden, a kind of message. The way the gravitational waves fade, the precise pattern of their weakening, carries within it the mass of the final black hole, and its spin, like a fingerprint pressed into the fabric of space, a signature that tells us exactly what was born in that moment of collision, and then silence. But let us leave the merging of black holes behind now and travel much further back, to the very beginning. There is a possibility, one that has quietly occupied the minds of physicists for decades, that some black holes did not come from stars at all. In the first fraction of a second after the Big Bang, the universe was unimaginably dense. Matter and energy were pressed together so tightly that in some regions, the density may have been enough, all on its own, to collapse inward. No star needed to burn and die. No supernova needed to thunder through space. Just the raw, immense pressure of the newborn universe, folding in on itself in small, scattered places. These are called primordial black holes. They may have formed in those earliest moments, when the cosmos was still smaller than a grain of sand, when everything that would one day become galaxies and stars and planets and you was compressed into a space almost too small to imagine. If they exist, some of them could be very small, far smaller than any black hole born from a dying star. And if they are small enough, something remarkable follows. They could be evaporating right now, slowly losing their mass through Hawking radiation, that faint quantum glow at the edge of the event horizon, growing just a little warmer, a little brighter, with each passing age. Some of them may have already vanished, returned entirely to the universe as a whisper of light and particles. Others may still linger, too small to see, too faint to detect, but present, scattered through the dark. And here is where the idea becomes even more quiet and strange. Some researchers have proposed that primordial black holes, if they exist in the right numbers and the right sizes, could account for some, or even all, of the universe's dark matter. Dark matter, that invisible substance we know is there because of the way galaxies rotate, the way light bends around clusters of galaxies, but which we have never directly seen, never caught in a detector, never held in a beam of light. It may not be a new kind of particle at all. It may be black holes, ancient ones, born before the first star ever shone, drifting unseen through the cosmos since the beginning of time. This remains an open question, a soft uncertainty at the edge of what we know. Now, between the black holes born from single stars and the supermassive giants that anchor entire galaxies, there is a middle ground, a category that has proven remarkably difficult to find. Intermediate mass black holes, those with masses between about 100 and 100,000 times the mass of our Sun. They should exist. The mathematics allows for them. And yet, confirming their presence has been one of the quieter challenges of modern astronomy. A few candidates have been found in the dense hearts of star clusters, where thousands of stars orbit close together, and in small, faint dwarf galaxies, where a modest black hole might sit at the center, gently pulling on the stars around it. But firm confirmation is rare. These black holes are too small to dominate their surroundings the way a supermassive black hole does, and too large to form in the simple collapse of a single star. They occupy a space between certainties. Let that settle for a moment. Now bring your attention a little closer to home. The nearest known black hole to Earth lies roughly 1,600 light-years away, in the constellation Ophiuchus, the Serpent Bearer, a pattern of stars visible in the summer sky. It is a quiet black hole, not feeding, not glowing, simply there, a dark companion drifting among the stars of our own galaxy. 1,600 light-years is a vast distance by any human measure, and yet, in the scale of the Milky Way, it is close, remarkably close, like a neighbor just a few houses down a very long street. And this raises a thought worth holding gently. A black hole with no companion star, one that is not pulling gas from a neighbor, not surrounded by a glowing disk of hot matter, would be nearly invisible. It would emit no light, reflect no light. It would simply move through space, dark and silent. The only way to find such a wanderer would be through gravitational microlensing, a subtle effect. When an unseen massive object passes between us and a distant background star, its gravity bends the star's light. For a brief time, the background star appears to brighten, not because it has changed, but because the hidden object in front of it is acting as a lens, focusing the light toward us, and then the brightness fades, and the wanderer moves on, unseen once more. A brief glow, and then nothing. Through this method, and through careful estimation, astronomers believe there may be as many as 100 million stellar mass black holes drifting quietly through the Milky Way. 100 million, each one dark, each one silent, each one carrying within it the collapsed remains of a star that once burned with light. They are everywhere around us, and we would never know. Let that thought rest now. Let it become part of the stillness. And turn your attention inward, not inward into yourself, but inward into the black hole, past the event horizon, into the place from which nothing returns. Inside a black hole, time moves in only one direction, toward the singularity. In the same way that here, outside, time carries us always forward, never backward, never pausing. Inside the horizon, that forward motion of time becomes a forward motion in space, always inward, always deeper. If you could somehow send a signal outward from inside the event horizon, a beam of light, a radio pulse, a message of any kind, it would not travel outward. It could not. Even light, moving at the fastest speed the universe allows, would find that every direction it travels leads inward toward the center, toward the singularity. The geometry of space-time itself has closed around it, like a river whose every tributary flows the same way, and there is no upstream. And yet, for someone falling into a very large black hole, a supermassive one, with millions or billions of solar masses, the crossing of the event horizon might not feel like anything at all. There would be no wall, no flash of light, no sudden change. An observer inside might not realize they had crossed the boundary for some time. They might look around and see space stretching out before them. Curved, yes. Strange, perhaps, but open, traversable, quiet. The horizon is not a door that slams shut. It is more like a line drawn on still water. You cross it without a ripple, and only later do you understand that you can no longer go back. Let that image stay with you now. The stillness of a boundary you cannot feel. A threshold crossed in silence. And so you are inside now, past the horizon, drifting through a space that still feels like space, still and wide and strangely calm. The interior of a very large black hole is not the cramped and crushing place you might expect. It could contain a vast region of curved spacetime, warped, yes, bent by gravity beyond anything found elsewhere in the universe, but traversable, a place where distances still stretch out ahead of you, where light still moves, where moments still pass, one after another. It is a cathedral with no walls, only curvature, only the slow, patient pull of geometry folding inward. And if the black hole is spinning, if it carries the rotation of the massive star that made it, or the accumulated turning of everything it has ever drawn inside. Then the interior becomes stranger still. Some theoretical models suggest that deep within a rotating black hole, space-time may curve back on itself in a very particular way, forming what physicists call closed time-like curves. These are paths through space-time that loop, not through space alone, but through time. A traveler on such a path would, in principle, return to a moment already lived, not by moving backward, but by following the geometry of the universe itself as it bends into a circle. Let that settle gently. Paths that loop through time. It is a quiet idea, and a deeply strange one. And most physicists suspect it is not truly possible, that some principle we have not yet discovered forbids it, that the mathematics may allow it, but the universe does not. Closed time-like curves remain speculative, a whisper at the edge of what our equations can describe, beautiful on paper, but likely kept from the real world by a rule we have not yet learned to write down. There is a kind of honesty in that, in admitting that our deepest theories sometimes point toward things that may not be real, and that the universe may hold boundaries even our best mathematics cannot cross. And speaking of boundaries, there is a quiet conjecture in physics, one that has guided thinking about black holes for decades. It is called the cosmic censorship conjecture, and it proposes something almost poetic, that every singularity in the universe, every point where density becomes infinite and the known laws of physics break down, is hidden, tucked safely behind an event horizon, sealed away from the view of any outside observer. The universe, in this picture, is modest about its own extremes. It does not display its contradictions openly. It wraps them in darkness. A singularity without an event horizon is called a naked singularity, and it would be a deeply unsettling thing. It would mean the breakdown of physics could be seen directly, not shielded behind a boundary of no return, but exposed, raw, visible to anyone who looked. No naked singularity has ever been observed, and most of the mathematical solutions that produce them require conditions so extreme, so perfectly arranged, that they seem unlikely ever to arise in nature. The universe, as far as we can tell, keeps its deepest secrets covered. Let that thought rest for a moment. There is a way to see all of this: the horizon, the interior, the singularity, the paths of light and time, drawn out on a single page. It is called a Penrose diagram, named after the physicist Roger Penrose, and it is a way of mapping the entire causal structure of a black hole spacetime onto a finite drawing. On a Penrose diagram, the whole of an infinite universe is folded down into a shape you can hold in your hand. Every possible path a beam of light could take, every trajectory of a falling body is captured in the angles and boundaries of this quiet little map. And on such a diagram, for the simplest kind of black hole, a Schwarzschild black hole, one that does not spin and carries no charge, the singularity appears not as a point at the center, but as a horizontal line drawn across the top of the interior region. It lies in the future of every point inside the horizon, not a place you travel toward, but a moment you cannot avoid, like tomorrow. And yet, even the event horizon itself, that smooth, silent boundary we spoke of, may not be what it seems. In 2012, a group of physicists raised a troubling possibility. They suggested that quantum effects near the event horizon might create something unexpected, a wall of high-energy particles, searing and violent, right at the boundary. They called it the firewall. If firewalls exist, then the event horizon would not be the gentle, uneventful threshold that general relativity predicts. It would not be a line crossed in silence. It would be an ending, abrupt and fierce. This is the firewall paradox, and it remains unresolved. It sits at the very heart of the deepest tension in modern physics, the long, quiet disagreement between quantum mechanics and gravity. Two theories, each extraordinarily successful on its own, each describing a different face of reality with breathtaking precision. Yet, when brought together at the event horizon of a black hole, they seem to disagree about what happens next. No one knows yet which one is right, or whether both will need to change. Let that uncertainty be a kind of comfort. Even the deepest minds in physics are still listening for the answer, still waiting in the dark. And there are other possibilities, other ways the story might unfold. From string theory comes a proposal called the fuzzball. In this picture, the event horizon is not a boundary around an empty interior. There is no void inside, no hollow darkness stretching down to a singularity. Instead, the entire region is filled, replaced by a tangled, intricate ball of fundamental strings, vibrating softly, woven together in patterns of extraordinary complexity. In the fuzzball picture, there is no true interior at all. Everything the black hole contains is encoded on its surface, written into the structure of those tangled strings. And because of this, information is not lost. It is not swallowed into a place from which it can never return. It is held, gently, in the fabric of the fuzzball itself, like words pressed into the pages of a book that can, in principle, still be read. It is a strange and quiet idea that what looks like darkness from the outside might be, on the smallest scales, something rich and intricate and full. We do not yet know if fuzzballs are real. We do not yet know if firewalls burn at the horizon. We do not know if the singularity is truly there, or if something softer waits in its place. But these questions are still being asked by patient, careful minds, working slowly, in the same darkness we are all resting in now. Let the not knowing be gentle. Let it settle around you like a blanket. There is no hurry. The answers, if they come, will come quietly, in their own time. And in that gentle not knowing, another possibility has taken shape, quietly, in the mathematics of a theory called loop quantum gravity. It suggests that the singularity, that point of infinite density at the heart of a black hole, may not be there at all. Instead, something else may happen. A bounce? A quantum bounce, where matter, crushed beyond all familiar limits, does not collapse into nothingness, but reaches some unimaginable density and then rebounds. Slowly, over spans of time too long to hold in a single thought, the black hole transforms into something called a white hole. A white hole is a strange and beautiful idea. It is the time reverse of a black hole, a mirror image written in the same mathematics, but running the other way. Where a black hole is a region that nothing can leave, a white hole is a region that nothing can enter. Matter and light can only flow outward, pouring from its boundary like water from a spring that has no source you can reach. No one has ever observed a white hole. Not in the sky, not in any instrument, not in any signal we have learned to read. And yet, white holes are valid solutions of Einstein's equations. They are permitted by the same geometry that gives us black holes, the same curves of space-time, the same quiet mathematics. They are allowed, even if the universe has not yet shown us one. Or perhaps it has shown us one, and we simply did not recognize it. Because some models, careful, tentative models built by patient hands, propose something extraordinary. They suggest that our entire observable universe, everything we have ever seen or measured or touched, every galaxy, every photon, every grain of dust, could have originated from a bounce deep inside a black hole in some larger cosmos we will never see. That what we call the Big Bang, that first moment of expansion, may have been the other side of a collapse. A star, perhaps, in a parent universe, falling inward, reaching that unthinkable density and bouncing outward into everything we know. It is only a possibility, a whisper at the edge of what our theories can describe, but it is a possibility that the mathematics allows, and there is something deeply restful about it. The idea that even endings might contain beginnings, that even the deepest collapse might open, somewhere, into light. Let that thought drift. You do not need to hold it. Let it settle where it will. And now, let us return to what we have seen, to the black holes we have actually found, the ones whose presence we have measured and confirmed. In the galaxy M87, 55 million light-years from where you are lying now, there sits a black hole of almost incomprehensible mass, about 6.5 billion times the mass of our Sun, gathered into a single dark region of space-time. Its shadow, the dark silhouette cast against the glowing gas that surrounds it, is roughly the size of our entire solar system, that vast, familiar space. From the Sun to the outermost reaches, where the solar wind fades into the interstellar dark, all of it would fit within the shadow of that one quiet object. This is the black hole whose image was captured in 2019, the first time human eyes ever looked upon the shape of an event horizon's edge, rendered in soft orange light by radio telescopes spanning the Earth. But M87's black hole was not the first to be found. That story begins closer to home, and a few decades earlier. In the early 1970s, astronomers turned their attention to a powerful source of X-rays in the constellation Cygnus. They called it Cygnus X1. It was a binary system, a massive blue star locked in orbit with something unseen, something heavy, something that pulled gas from its companion and heated it to millions of degrees as it spiraled inward. The unseen companion was too massive to be a neutron star, and it emitted no light of its own. Slowly, carefully, the case was built, and Cygnus X1 became the first widely accepted black hole candidate. It was the subject of a famous wager. Stephen Hawking bet against it being a black hole, and Kip Thorne bet that it was. A gentle, good-natured bet between two minds who understood the stakes better than anyone. Hawking conceded in 1990, years after the evidence had grown too strong to resist. Even he, it seems, could be quietly surprised by the universe. Since then, we have found black holes of many sizes. The smallest known are only about 3 to 4 times the mass of our Sun. Compact, dense, born from the deaths of stars that were large but not the largest. And there is something curious in the numbers. There appears to be a gap, a range of masses between roughly 2 and 5 times the mass of the Sun, where we find very few objects. The heaviest neutron stars sit just below this range, and the lightest black holes sit just above it. This mass gap may be explained by the physics of supernova explosions. By the way, a dying star's core either holds together or doesn't, though some recent detections have begun to challenge its boundaries, placing objects in that uncertain middle ground where our categories blur. The universe, it seems, does not always sort itself as neatly as we might wish. And here, as you rest, let one gentle correction settle into place. Black holes do not suck. They do not reach out and pull things in like a drain in a bathtub. They attract matter gravitationally, just as any other mass does, just as the Earth holds the Moon, just as the Sun holds the Earth. It is only at the event horizon that gravity becomes inescapable. Only there does the path inward become the only path. From a distance, a black hole is simply heavy and quiet and still. And if you were far away, watching a clock fall toward 1, you would see something strange and slow and beautiful. The clock's hands would begin to lag. At first, only slightly, a fraction of a second lost here and there. But as the clock drifted closer to the horizon, the slowing would deepen. The hands would creep, then barely move, then seem to hover, trembling at the edge of stillness. You would never see them stop. Not quite. They would slow, and slow, and slow, approaching a moment they would never reach. The clock would fade as its light stretched to longer and longer wavelengths, reddening, dimming, until it slipped beyond what any eye or instrument could detect. And then, silence. Not because the clock was destroyed, but because its light could no longer climb back to you. It crossed a boundary, and from your side of that boundary, it simply, quietly, disappeared. This is what time looks like near a black hole. It stretches, it softens, It thins like mist at the edge of morning. And you, lying here now, are also moving through time, gently, one breath at a time, one slow heartbeat after another. There is nowhere you need to be. The clock beside you can slow as much as it likes. Let it. And on the other side of that vanishing, something stranger still is true. Inside the event horizon of a simple black hole, the kind Carl Schwarzschild first described, the singularity is not a place. It is not a point in space you travel toward the way you might walk toward a door. It is a moment in time, a moment in the future. The singularity waits for you the way tomorrow waits for you, not somewhere ahead in the distance, but somewhere ahead in the clock, unavoidable. Not because you are moving toward it, but because time itself carries you there. Every direction you could turn, every path you could take, leads to the same moment, the way every road through an evening leads eventually to night. This is perhaps the strangest thing about the inside of a black hole. Space and time trade their roles. Moving forward in time means moving inward, and there is no turning back. Not because the walls are closing in, but because the future only flows one way. And yet, even this is not the end of the story. Because a black hole does not last forever. Nothing does. In 1974, Stephen Hawking showed that black holes are not perfectly black. They glow, faintly, impossibly faintly, with a warmth so slight it is far colder than the faintest whisper of the cosmic background. This is Hawking radiation, a quiet consequence of quantum behavior near the event horizon. Particles flickering into existence in pairs, one falling inward, the other drifting free, carrying away the smallest imaginable trace of the black hole's energy. It is almost nothing, but almost nothing, over an unthinkable stretch of time, becomes everything. A stellar mass black hole would take roughly 10 to the power of 67 years to evaporate this way. That number is so large, it has no meaning in human terms. It dwarfs the current age of the universe the way an ocean dwarfs a single drop of rain. But time is patient. Time does not tire. And slowly, so slowly that no instrument could ever measure the change from one eon to the next, the black hole loses mass. It grows lighter, warmer, smaller, returning what it once gathered, particle by particle, back to the universe that made it. Every black hole will do this. Every one. The small ones and the vast ones. The ancient black holes born from the first collapsing stars, and the supermassive ones sitting quietly at the hearts of galaxies. All of them, given enough time, will give back everything they hold, leaving nothing behind. Not a shell, not a scar, not a shadow, nothing. But before that final silence, there is a long and extraordinary era still to come. In the far future, after the last stars have exhausted their fuel and cooled to darkness, after the white dwarfs have faded, after the neutron stars have grown cold, black holes will remain. They will be the last large objects in the universe, drifting through an emptiness so vast and so dark that the age of starlight will seem like a brief, bright morning, long since past. This era, the age of black holes, is expected to last from about 10 to the 40th year to 10 to the 100th year after the beginning of everything, a span of time so deep that the entire history of stars, all of it, every galaxy, every nebula, every sunrise on every world, fits into its earliest, most fleeting instant. And through all of that darkness, the black holes will sit, slowly, quietly, radiating their faint warmth into the void. One by one, they will grow smaller. One by one, they will fade. The largest ones will be the last to go, those ancient supermassive black holes, patient beyond all reckoning, holding their mass like a breath held for longer than the stars could dream. But even they will exhale. And when the last black hole finally releases its last particle of light, the universe will enter a state of near perfect emptiness. A cold so deep it approaches absolute zero. A stillness so complete that nothing moves, nothing changes. Nothing remains to mark the difference between one moment and the next. No stars, no light, no warmth, just space stretching on and on and on. And yet, even this is not quite despair. Because what the black holes teach us, what their long, slow, fading whispers across all those incomprehensible years, is that even darkness lets go. Even the deepest gravity, the strongest hold anything in the universe can exert, is not permanent. Given enough time, even a black hole opens its hands. Given enough time, everything is returned. Quietly, without ceremony. The way snow melts in early spring, not all at once, but so gently you cannot say exactly when it became water. Even darkness, it seems, is not forever. And you, here, now, in your own quiet room, in your own small corner of this vast and patient universe, you are held by nothing stronger than the softness of your bed and the slow pull of sleep. Let it carry you, the way time carries all things. Gently. There is nothing left to hold on to, and that is enough.